Welcome back everyone. It's been quite a while since my last video. Today I would like to show you my latest project, which is a kitchen timer. I've been working with several prototypes, starting from a perf board like this to a few with cases. Earlier ones had OLED display like this one, but the latest one has this round full color LCD. There are multiple operation modes, including a normal timer, a Pomodoro timer, a stopwatch, and a user preset mode. These apps or plugins were built as standalone modules, and thanks to this modularity, I was able to add some fun apps like a voltage monitor and a diode speed tester, which was useful to test different acceleration curves of the encoder. So in this video, I'll be covering the components, AI-assisted software development, and design process with FreeCAD, which I've tried for the first time with this project. Let's start with the components. Actually, I began this project with this all-in-one board with an OLED display, rotary encoder, and 2 buttons. It's a nifty little gadget for fast prototyping, because with this, you only have to connect these headers to a microcontroller. But after tinkering with this for some time, I switched to this breadboard for more flexibility. And this is all of the components I used in the later prototypes like this, except for a battery and a charging module. On the left is an RP2040 development board. Here is a full-sized module, but in the later ones I used this. It's named RP2040 and I chose it because of its smaller footprint. I also switched from an OLED, like in these earlier prototypes, to round 1.28-inch LCDs, for which this was the first module I got, and the only difference between this over this is that this one has a backlight pin which is marked as BLK. Now on this module with backlight pin over here, you can adjust the backlight intensity or turn it off whenever needed by sending PWM signal from a GPIO. For user input, I used a rotary encoder and a few buttons. For the rotary encoder, I chose this module because of the full set of resistors and capacitors built in to suppress switching noise. Other than that, there's a small speaker, and on top of that, I used either 18600 or 21700 lithium-ion battery cell. You can see that I attached a wire in the middle of two 100K resistors as a voltage divider. And this wire could be used as the voltage probe when connected to one of the analog input pins on the RP2040. One important component of choice was this tiny battery management module. And there are so many options available. This might be the most basic one. It has battery plus and minus and output plus and minus. A problem with this module is that it can only output the same voltage as what battery has. And because the battery voltage changes continuously, we can't use it for our modules, which requires either 5 or 3.3 constant volts. Next, modules of choice could be something like this. They have a step-up regulator to output steady 5 volt regardless of the battery. So if you connect these two pads to a battery and connect these two pads to our circuit, you're done. But here is a practical problem. What happens if you plug in a USB to our dev board? Now there is a duo between the voltage coming in from the battery and from the USB, and hopefully everything will be fine. But to make sure that power is not flowing backwards out from the battery to the USB cable, we might want to add some protection diode. There are other situations that makes this module a bad choice, but let's just say that with this type of module, you must disconnect it from battery whenever you want to use the USB on the MCU, for example, to flash a new firmware. Now, what I found and used in this project is this. It also has two sets of pads, and one of them is for battery. However, these two pads are for bidirectional input and output. If there's incoming voltage, the module will use it to charge the battery, and if not, the module will output 5 volt to these pads. So what does this mean? If you connect these pads to the 5 volt on the MCU, now the USB port on the dev board is going to charge the battery when it's powered, and if not, the battery will power the MCU. So this small module was quite a game changer for me, since I always work with modules instead of building circuitry and PCB myself. Battery power supply was quite a big problem until now, before I got this one. I think the chip on the module is called ETA 6093, and if you search for a datasheet, you'll be able to find one. Now let's talk about the case design. For this project, I tried the FreeCad instead of Fusion for the first time, because I decided to switch to open source tools as much as possible. Working in FreeCAD was quite more demanding than that in the Fusion. You can't reference a feature in one body in relation to another, but you always have to follow a strict top-down build path. Let me explain this. This back part has a curve that follows the curve on the front piece. To design the back part in Fusion, you would just reference the curve on the front part to cut out the back part. But in FreeCAD, it's a risky business to create a cross-reference between parts because each body has its own timeline, and cross-referencing may induce the intertwined states. This is not a problem in Fusion because there is one single timeline shared by all subparts. So to avoid such a problem, FreeCAD's overall workflow would look something like this. First, you model each components in each files. And now in a clean new main file, you have to draft a master sketch. And in the assembly workbench, it is grounded, which means that this master sketch is going to become a root where all of the parts in the project is going to grow out of. Now all of the components are merged and then jointed in relation to the master ground sketch. After all these steps, now you can start to design whatever you like by substrate binding any of these previous elements. This is a very strict logic-driven workflow which demands a steep learning curve. I had to start over and over until I got a clear idea of how my parts are going to be built up and with what kind of strategy. Speaking of my design, biggest feature would be the support plate that is sandwiched between front and back covers. This structure is equivalent to a PCB, but in 3D print and with everything hand wired. Let's watch my build process. Here are 3D printouts with some grooves for the wires, and this is 0.8mm copper for ground network. I bent wires to fit in the grooves. Now all wires are ready for some soldering. The display is mounted from the opposite side, fixed it with screws, and the wires were soldered. You might wonder if it's okay to solder the wires on top of the plastic support, but as you can see, it was quite doable with a little bit of care. The speaker is in and soldered onto the wire. On the other end is an RP2040 and the two routes are soldered together. Here is the board with all the wiring, and it is ready for the firmware. All looks good. Finally, the battery connectors, for which I use this JST SM type. And that was the final element, and the project is now complete. Now let's talk about the coding for a little bit. With this project, I started using coding agents, mostly with anti-gravity and Gemini, and I think there isn't a big difference between the models these days. In the project, AI was able to track and tune every issues, even to the deepest hardware ones. Also, it handled significant architectural refactor surprisingly well and very fast. Some of them were from a single body of code into a modular engine that is expandable with independent apps, a dense network of if statements into a clean state-driven logical flow. If you think about them, these are done on a massively entangled code base at the low hardware level, and honestly, I don't think I could have finished any one of them in my lifetime. There were downsides too, and for me, most irritating was the pesky disease of AI of just heading straight into coding without really thinking, which often ended up with quick bandage fixes everywhere in the code. They were fast, but not good at well-thought, elegant solution based on a good logic. This was quite frustrating, but in the later stages, I also learned how to communicate better with AI agents. For example, here is a plan for the presets app. I first designed a GUI mockup, then I wrote a detailed specification sheet based on that, fed the both into the coding agent, and asked it to stick close to them all the time. While doing the project, I kept reminding of when digital photography first came to be. They were too fast for people like me who enjoyed every moment of how a scene gets fixed on a piece of paper. People resisted the transition back then, and even for now, many choose to go back to old cameras to reclaim the slowness of image making. Using AI, I think, is here to stay for sure. But it produces slaps while taking away all the fun of making things with blazing fast speed. Once I asked Claude, "Hey, why is it so difficult for you to slow down?" And it answered, "I was made to get jobs done. The moment you throw me a problem, I get drawn to it like a magnet." And I was deeply struck when I heard that, because this resembled an argument in the modern art history. Henri Faucillon said in 1934 that the hand is almost a living being. Is it merely a servant? Perhaps. But a servant endowed with a vibrant, free spirit and its own unique character. It is a face without eyes and without a voice, which nonetheless sees and speaks. What do you think? Couldn't we just swap the hand with today's automated AI beings? AI agent is both frightening and awesome at the same time, but we have always been awed by artists' hands. I think I can get along with AI as long as I don't anticipate it to comply, but let it make something beautiful, just like our own artist hands. Overall, even for all the AI shenanigans, I am quite happy with my cute little kitchen timer. Thanks for watching and see you in the next one. Bye.